Welcome back to The Explainer, produced by Forge College. So, in our last lesson, Economic Incentives and Value in Web3, we built this mathematically flawless, pristine economic engine, right? Well, today we're running a stress test. As part of our broader dive into transitioning to Web3 within the blockchain fundamentals track, we're taking that shiny new engine and dropping it right into a messy, chaotic, and highly unpredictable real-world chassis. Let's see if our perfect theories can actually survive contact with reality, without bursting into flames.
To do that, we've got a pretty packed engineering blueprint today. We're going to kick things off with a quick Web3 reality check, then dive into the physics of speed, size, and forks. After that, we'll weigh the sharding trade-off, figure out who actually rules the network, talk about resisting censorship, and wrap it all up by engineering some real-world mitigation.
All right, let's jump right into part one, the Web3 reality check. We've really got to bridge the gap between theory and practice here.
It's kind of funny when you look at this stark contrast between these two. I mean, theoretically, our ideal economic engine just happily assumes perfect throughput, instant finality, and that literally everyone has broad access. But then you hit the real-world chassis. Suddenly you're bound by network latency, physical bandwidth limits, and, oh yeah, human politics. It's pretty simple. If your underlying technical primitives and social conditions are weak, all those brilliant token incentives just won't matter. Your beautiful engine won't hum. It'll just sputter and die.
Which brings us to the literal physics of our Web3 machine: speed, size, and forks.
To really grasp this, we have to talk about something called the fork rate. This is basically the frequency at which the main chain gets forced into a reorganization. Picture this. You've got two validators on complete opposite sides of the globe, and they both shot out their newly proposed blocks at the exact same millisecond. The network hears both, gets completely confused, and basically has a momentary identity crisis, trying to figure out which one to accept. What this tells us is that you can't just crank the speed dial up to 11 and expect things to work out. It just causes absolute chaos.
Because whenever you tweak the system's parameters, physics pushes back hard. For instance, based on our Python simulation data, if you go for a shorter block interval, sure, blocks are proposed faster, but you get a way higher probability of forks and much weaker finality. What about a longer propagation delay? Naturally, that means more simultaneous proposals, which, again, means more forks. And if you think, hey, let's just increase the block size to cram more data in, well, larger blocks take way longer to serialize and send across the network. That basically replicates a long propagation delay, skyrocketing your fork risk. It's kind of like trying to shove a bowling ball through a standard garden hose. Something's definitely going to break.
So the absolute crucial takeaway here is that scalability choices aren't just some magical increase bandwidth button you can press. When you pull one lever, you are fundamentally changing the entire machine. Changing just a single technical parameter creates these wild, nonlinear effects that completely alter your consensus dynamics and eat into your security margins. You have to actually quantify these things, not just assume they'll work out.
Okay, so how does this play out when we try to divide and conquer the workload? Let's look at the sharding trade-off.
This is an architectural choice we constantly explore in our learning programs at Forge College, and honestly, the math is incredibly sobering. Let's say you have a network of 100 validators and you slice it into 5 shards so you can process transactions in parallel. Well, now you only have 20 validators per shard. You've just massively diluted your security. It's literally like splitting your night watchman up to cover more doors. Suddenly, each door is a whole lot easier for the bad guys to kick in. And the trade-offs just keep piling up. As the number of validators per shard drops, your fork rate naturally rises. You're demanding complex cross-shard messaging and really robust finality mechanisms to keep it all together. Eventually, the sheer nightmare of coordinating all these separate shards completely outweighs the benefits of running things in parallel. It creates this hard engineering limit where the operational costs just devour any of your expected throughput gains. But we've talked a ton about code and math so far. Here's the ultimate curveball, though. Let's say your code is 100% flawless. At the end of the day, this machine is still operated by human beings, which brings us to a massive sociological stress test. Who actually gets to make the rules? Let's step into governance and figure out who is really running the network. Because governance is what determines who makes the system-changing decisions and exactly how they go about making them. We usually see two main models here, and honestly, they both have their own unique flavor of danger.
On the one hand, you've got on-chain token voting. It's incredibly transparent and verifiable, but it completely risks handing the keys to the castle over to giant token holders, or whales. On the other hand, you have off-chain representative councils. They can act super fast in an emergency, like a corporate board in a smoky back room, but they often entirely lack democratic legitimacy and broad inclusion. It's super ironic when you think about it. The exact same tokens used to reward people for growing the network can ultimately just centralize veto power. Incentives and governance are permanently intertwined. So to avoid disaster, we have to deconstruct these governance rules into three main buckets. The what, meaning the actual proposal or network upgrade. The who, as in who are the eligible voters or signers. And the how, what are the rules for quorums, supermajorities, and veto thresholds. Breaking it down like this is brilliant, because it makes it so much easier to spot where a system might get captured. And once you spot the risk, you can design smart mitigations, like requiring a diverse, multi-stakeholder quorum before anyone can push a major breaking change. Now, all that governance stuff is great, but it brings us to resisting censorship and preventing exclusion entirely. Because frankly, a perfectly governed network is completely useless if nobody can access it, or if it can be easily silenced. Here's the harsh truth of Web3. Decentralization is nothing more than a nice theory if heavy resource requirements or a nightmare user experience exclude everyday people. Think about it. If it takes a $100,000 supercomputer and a PhD to run a network node, your network is naturally going to concentrate influence into a tiny, technically elite club. That isn't decentralization. That's just centralization by default. Inclusion is a technical issue just as much as a procedural one. And when you lose that broad inclusion and become centralized, you become highly vulnerable to censorship across three very distinct layers. First is the technical layer, where validators or miners could just refuse to include your transactions. Second is the infrastructure layer, where cloud services or ISPs could unplug the activity entirely. And third is the social and legal layer, where exchanges or legal entities put pressure on the network. If you want to truly resist censorship, you have to ask yourself, how many of these layers does an adversary actually need to compromise to shut us down? The more independent your relays and alternative access paths are, the stronger your practical resistance is going to be. All right, so we've identified the limits and the stress points. How do we actually engineer the solutions? Here is your Web3 blueprint checklist to take away from this explainer. 1. Always measure your fork rates before you go messing with block parameters. 2. Monitor validator drops the very second you introduce sharding. 3. Balance your on-chain voting with constrained delayed upgrade windows, just so the community actually has time to react. 4. Aggressively lower hardware requirements using light client designs so everyday laptops can join in. And 5. Implement multi-relay propagation for that sweet censorship resistance. You see, a real engineer doesn't just shout, "We need scale!" Instead, they propose increasing block intervals while adding parallel execution, and then they pair all of that with crystal-clear governance safeguards. It really all comes down to this idea. Practical mitigation strategies require both technical and procedural elements. You need code changes, plus governance safeguards, plus onboarding improvements. You simply cannot solve a human social problem with just a clever line of code, right? And on the flip side, you definitely cannot solve a physical network latency problem by just holding a community vote. The two worlds have to work in tandem. Technical upgrades require procedural safeguards, and governance requires rock-solid code to actually enforce it. So I'll leave you with this final thought. Which technical primitives will you engineer to overcome these real-world bottlenecks? Keep that question rolling around in your mind as we head into our next explainer in the track, which will be on the foundations of decentralization. Thanks so much for joining me today. Please make sure to visit forge.college to learn more about this subject and to keep exploring the messy, fascinating world of Web3. See you next time.